What's going on, everybody? Got another video here for you. It's statistics, probability rules of compound events. We're going to be looking at probabilities involving and or. All right, so we've got two events are independent if the occurrence or non-occurrence of one event does not change the probability that the other event will occur. All right, so independent events, if I'm going to find the probability of something and I find the probability of this one event and then I find the probability of this other event and the probability of them both happening, if the probability of this first event does not affect the probability of the second event, then they're independent. But if the probability of the first event affects the probability of the second event, then they're not independent. All right, so let's look at these rules here. We've got multiplication rule for independent events is the probability of A and B equals the probability of A times the probability of B. Now, look at the notation I use here. I use probability of A and B. You may see it written as probability of A and B. You may see this notation also. Actually, the book I'm using, it uses this notation right here. But I went ahead and did it like this because it was easier for me to type up like that. That's why I did that. All right, so basically all you're doing is multiplying the probability of the two events together. All right, and then the general multiplication rule for any events is the probability of A equals the probability of A. The probability of A and B is equal to the probability of A times the probability. All right, now let's look at this. What is this? How do you read this? The probability of B given A. Or you can have the probability of A and B is equal to the probability of B times the probability of A given B. All right. So all this means is the probability of A and B is equal to the probability of A times the probability of B given that A has occurred. All right, that's how you would read it. And if you look at this, we can take, you can just take this one right here, and if you divide both sides by the probability of B, then you've got the probability of A given B by itself is equal to the probability of A and B divided by the probability of B. See, if we divide both sides by the probability of B, basically you get this one down here for conditional probability. So conditional probability, the probability of A given event B has occurred is the probability of A and B divided by the probability of B. All right. So looking at that or knowing those rules now, let's go ahead and look at some examples. All right, we've got a lot of examples to work in this video, which is good. All right. So it says, suppose you're going to throw two fair dice. What is the probability of getting a 5 on each die? All right, so die, that means 1, dice means 2, or dice means 2 or more. All right, so how are we going to go about doing this? Well, we want a probability on, say, the first die. We want the probability that we get a 5 on the first die, and we want a probability that we get a 5 on the second die. All right. So, well, what is the probability? The probability 5 on first die and 5 on second die. Well, what's the probability that we get a 5 on the first die? Well, there's 6 numbers on the die, right? 1 through 6, and there's 1 5 on there. So that's going to be 1 over 6. So this is the probability of getting a 5 on the first die, and so we got times a probability of getting a 5 on the second die. Well, that would be 1 over 6 also, and that would be 1 over 36. That would be our probability. All right. So easy enough. All right, let's look at this one. Consider a collection of 6 balls that are identical in color, that are identical except in color. Okay, let's start over on that one. Consider a collection of 6 balls that are identical except in color. There are 3 green balls, 2 blue balls, and 1 red ball. Compute the probability of drawing 2 green balls from the collection if the first ball is not replaced before the second ball is drawn. All right. So, how are we gonna do that? All right. So we want the probability of 2 green. Now, this is without replacement. So we've got 6 balls, probably in a container, and we're going to reach in there and choose 1 ball. So what's the probability that we get a green ball on that first draw? Well, there's 3 green balls, so that's 3, divided by the total number of balls, which is 6. Remember, probability, it's the number of successful outcomes divided by the number of possible outcomes. All right, so this is our probability of getting a green ball on the first draw. All right, now we're going to reach in there and grab another one. So times, what's the probability that we get a green ball on the second draw? Well, that's going to be 2 over 5. Okay, so what happened here? All right, so on the first draw, the probability was 3 divided by 6. There's 3 green balls and there's 6 total. We drew a green ball out. So now, since 1 green ball is gone, that means there's only 2 green balls left and 5 total because we didn't put it back. And so that's where the 2 out of 5 come in. 2 over 5 comes in. And when we calculate that, we get 1 over 5. Because the 2 and 6 cancel. And that would leave us with 3, and the 3 and the 3 cancel. And so we're left with 1/5, which is 0.2. All right. Now, let's just suppose that we wanted to know this same probability of getting 2 green balls, but we're replacing the ball before we draw the second one. So, in other words, we draw the first ball out. And it's green. We put it back, and then we draw the second ball. So that probability, okay, so this is separate. We finish answering this question. I'm just doing a different one now. Okay, this was not replacing the ball. Now let's do it with replacing the ball. I know it's not part of the question, but let's just go over it. So that's going to be 3 over 6. That's the probability of getting a green ball on the first draw. There's 3 green, 6 total. And then we want a green on the second. So that would be 3 over 6 also, because we drew the first ball out. We drew the first green ball out. That probability was 3 over 6. And then we're taking that ball and we're putting it back in the container mixing them up, and then we're drawing another ball. So there's 3 green balls and 6 total because we replaced it. And that would be 9 over 36, which is 1/4, which is 0.25. And, and that makes sense. The odds are, the probability's higher of doing it this way because we're putting the ball back. Okay? All right. Let's look at this next example. All right, it says Andrew is 55, and the probability that he will be alive in 10 years is 0.72. Ellen is 35, and the probability that she will be alive in 10 years is 0.92. Now, makes sense. She's younger. Assuming that the lifespan of one will have no effect on the lifespan of the other, so they probably don't know each other, what is the probability they will both be alive in 10 years? All right. So we will just call Andrew, we'll call him event A, and we'll call Ellen event B. So we want to know the probability that Andrew and Ellen will be alive in 10 years. So the probability of A and B. Okay. We just called Andrew being alive in 10 years A, Ellen being alive in 10 years B. It's just easier to write down. You could write Andrew alive in 10 years and Ellen alive in 10 years. Okay, if that's what you want to do, that's fine. And so this is going to be the probability of A times the probability of B. We just multiply them together. And so that's 0.7, I was fixing to write a 5, 0.72 times 0.92, and that is going to equal 0.66. And so that's the probability that they will both be alive. Okay. All right. And these events are independent. Andrew's lifespan does not affect Ellen's, and Ellen's does not affect Andrew's. Okay. And plus, we know that because it tells us that right here will have no effect on the other. Okay. I guess there could be a situation where they do affect each other if they know each other and one person's doing something bad to the other or something like that. All right. So let's look at this next example. This is involving and then we're fixing to get into or. Okay. All right. So it says a quality control procedure for testing ready flash disposable cameras consists of drawing 2 cameras at random from each lot of 100 without replacing the first camera before drawing the second. Okay. So when we draw the first camera, we're not going to put it back. We're going to keep it out. That goes back to the example I worked earlier with the balls. Okay. If both are defective, the entire lot is rejected. Find the probability that both cameras are defective if the lot contains 10 defective cameras. Since we're drawing the cameras at random, assume that each camera in the lot has an equal chance of being drawn. Okay. So the lot contains 10 defective cameras. There's 100 cameras in the lot, and we want to know the probability of drawing 2 defective cameras. Okay. All right. So this is going to be the probability that first camera is defective and second camera is defective. Okay, that's what we're looking for. Okay, so this is going to be the probability that the first camera is defective times the probability the second camera is defective. Okay, So what's the probability that the first camera is defective? Well, there's 10 defective cameras in the lot, and there's 100 total cameras. So that would be 10 over 100. So that's the probability that the first camera is defective. And so times the probability the second camera is defective. So what's the probability that I get a defective camera on the second draw? Well, there's 9 defective cameras in there now because the first draw was a defective camera. Okay, so 1 defective camera's out of the lot. And now how many total cameras are in the lot? Well, there's 99 because we didn't put that defective camera back. And so this ends up being 1 over 110, which is equal to 0.009. Okay, so it's not a very high probability that we're going to draw 2 defective cameras. All right, so hopefully all this is making sense. Okay, so let's move on. All right, now let's talk about or. Okay, so 2 events are mutually exclusive or disjoint if they cannot occur together. In particular, events A and B are mutually exclusive if the probability of A and B equals 0. So that means they have nothing in common. Okay, now remember earlier when I told you about this probability of A intersect B, that was the same thing as A and B? Well, that's the same thing here. This probability of A union B or A or B, I can also write that as the probability of A or B. Like I said, you'll see it written like this too, and this is how the book does it, but I just used the union symbol because it was easier to type up. So the addition rule for mutually exclusive events A and B is the probability of A or B is equal to the probability of A plus the probability of B. So you add them together. Now, and that's for mutually exclusive events. Okay, that means they have nothing in common. But the general addition rule for any events A and B is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So you got to subtract out what they have in common. Okay, and I'll explain that. I'll explain that more as we work some of these examples. I'll explain to you why we're subtracting this off, and hopefully it'll make sense. Okay, all right, so let's look at some examples involving that. All right, consider an introductory statistics class with 31 students. There are 15 freshmen. 9 of those freshmen are female and 6 are male. 8 sophomores, 3 female and 5 male. 6 juniors, 4 female and 2 male, and 2 seniors, 1 female, 1 male. Suppose we select one student at random from the class. Find the probability that the student is either a freshman or a sophomore. All right, so if you look at this, you can see that these events are mutually exclusive because you can't be a freshman and a sophomore at the same time. You're one or the other. Okay, so those can't occur together. Those can't happen together. So they're mutually exclusive or disjoint. They have nothing in common. All right, so the probability, let's see, a freshman or a sophomore. I'm going to just use F for freshman, S for sophomore, and let me make a note of that. So for freshman, I'm going to use the letter F. For sophomore, I'm going to use the letter S. For junior, I'll use the letter J. And for senior, well, maybe we don't want to do that. I'll tell you what, we'll use SO for sophomore and S for senior. Okay, so the probability that we select a freshman or a sophomore. Okay, so that's just the probability a freshman plus the probability a sophomore. All right, so what's the probability that we select a freshman? Well, remember, probability, that's the number of successful outcomes divided by the number of possible outcomes. So there's 15 freshmen and 31 students total, okay, from right there, plus the probability a sophomore. Well, there's 8 sophomores and there's 31 students total. And so this is equal to 23 over 31, which that is 0.742 is our probability. All right. All right, so let's look at part B. Select one student at random from the class. What is the probability that the student is either a male or a sophomore? Okay, so the probability male or a sophomore. So that's the probability male plus the probability a sophomore. Okay, so let's talk about this for just a second. All right, so let's do this. Probability a male. Okay, so looking at that, how many male students are there? Well, let's see. There's 6 plus 5 plus 2 plus 1. So 6, 11, 12, 13, 14. There's 14 male students. So that's 14 over 31 plus, now how many sophomores are there? Well, there's 8. So that's 8 over 31. All right. Now look what happened here. I want you to understand why we're subtracting this off. Okay. These events are not mutually exclusive. Okay. Because think about it. Either a male or sophomore. Can you be male and a sophomore at the same time? Yes. So they're not mutually exclusive. All right. Now, this is why we're subtracting off what they have in common. We have to subtract off the probability of M and a sophomore. So look what happened here. So when we counted the males, we counted the 6 here, the 5 here, the 2 here, and the 1 here. Now look at this right here, this 5 here. Okay, we counted this 5. That's in this 14 here. But look at this. Also, when we counted the sophomores, the 8, that 5 is in that 8. So it's like we counted that 5 twice. So now we have to subtract that out. So what's the probability male and sophomore? Well, how many sophomore males are there? Well, there's 5 of them. So we have to subtract off 5 over 31. And that is equal to 17 over 31, which is equal to 0.548. And there's your answer. Okay, so I hope you understand that, why we're subtracting that off now, because we counted it twice. They're not mutually exclusive. Okay, they're not mutually exclusive. They have something in common there. Okay. All right, let's look at this next example. It says a clothing store carries slacks. If you buy a pair of slacks in your regular waist size without trying them on, the probability that the waist will be too tight is 0.3, and the probability that it will be too loose is 0.7. If you choose a pair of slacks at random in your regular waist size, what is the probability that the waist will be too tight or too loose? All right. So if we look at this, are these events mutually exclusive? Well, they are, aren't they? If you think about it, if you go buy a pair of pants, can they be too loose and too tight at the same time in your waist? No. They're either too loose or they're too tight. So the probability of tight or loose, that's what we're looking for. That's the probability that the pants are too tight plus the probability that the pants are too loose. All right, so let's see. Too tight, that's 0.3. They go ahead and give us the probability plus the probability that they're too loose, which is 0.1. So that is equal to 0.4. All right, let's look at the next example. I think we're almost, we've got this example and one more and we'll be done. So if you're still watching, hang in there. Okay. All right, Professor Jackson is in charge of a program to prepare people for a high school equivalency exam. Records show that 80% of the students need work in math, 70% need work in English, and 55% need work in both areas. Find the probability that a student selected at random needs work on both math and English. All right. Well, I typed this problem up wrong. This shouldn't say in both math and English. It's supposed to just say in both areas. Okay. All right. So how are we going to do this? All right. So we want to know the probability that they need help in math or English. That they need help in both areas. So are they mutually exclusive? No. Because you can need help in math and English, can't you? You could need help in both areas. And they actually give us that probability, 55% in both areas. So this is going to be the probability that we need help in math plus the probability we need help in English minus the probability that we need help in math and English. All right. And so here we go. Records show 80% of the students need help in math, so that's 0.8, plus the probability that they need help in English, that's 70%, so that's 0.7, minus what they have in common, the ones that need help in both, because remember, they would be counted twice, and that's minus the 0.55. This right here, they need help in both. And so this would be, what is this? Is that 0.95? Let me double check and make sure. So that's 0.8 plus 0.7 minus 0.55, and that is 0.95. So there's a 95% chance that they need help in both. How about that? All right. Last example, and we have a table here. All right. At Hopewell Electronics, all 140 employees were asked about their political affiliations. The employees were grouped by type of work as executives or production workers. The results with row and, that should be and, column totals are shown in the table below. Compute the following. Okay. All right, so we've got Democrats, Republicans, Independents, and we got executives and production workers. And so what this chart means is there's 5 executives are Democrats, 34 are Republican, and 9 are Independent, for a total of 48 executives. There's 48 total executives. And of the production workers, 63 are Democrat, 21 Republican, 8 independent, and there's a total of 92 production workers. And then these numbers down here, the 5 plus 63, that's 68. These are just these down here, that's the total of all the columns. And these two, this cell here and this cell here, that's the total of each of these rows. And then this right here, of course, that's if you add this up and if you add these three up, that'll equal the 140 total employees. All right. All right, so let's look at this. We want to know the probability of a Democrat. Okay. If we select these people at random, what's the probability that we select a Democrat? Well, how many Democrats are there? Well, there's 68 total Democrats. 5 of them are executives, 63 production workers, but there's 68 total Democrats. So that's 68 over 140, which that would equal 0.486. And then what's the probability of an executive? And by the way, the D, the E, all these letters here, that comes from here. The D and the E in parentheses, that's the abbreviation we're using for them. So what's the probability that we select an executive? Well, how many executives are there? Well, there's a total of 48 executives. So we got 5 plus 34 plus 9. See, all of these are executives, so there's 48 total. So that's 48 over the total number of workers possible, which is the 140. And so that is equal to 0.343. So there's the answer to the first part A. Now let's look at part B, the probability of a Democrat given an executive. All right. So look, the best way to do this is if you remember earlier in the video, let's see if I can go back up here and find it. Remember the conditional probability, this formula right here? Write it out. Just write this out. Okay? Just remember this second letter here, that probability goes in the denominator in the bottom here. It's just the probability of this and this divided by the probability of this second letter here. All right, so let's come back up here. Let's get back to the table. All right, so this is going to be the probability of, let me write it a little better, probability of D and E over the probability of E. And so what does this equal? Well, what's the probability D and E? That means the probability they're a Democrat and an executive. Well, here's the Democrat and executive. It's where they intersect. There's 5 of those. You see there's 5 executives that are Democrats. That says D and E. So that's 5 over the probability of an executive. Okay, well, how many executives are there? There's 48 total. There's 48. And so that would be 5 over 48, which is 0.104. Okay, now let me talk about this for just a second. You might be thinking, well, that 5 he wrote down, that's not a probability. That's not the probability of the numerator. And this 48 here, that's not the probability of being an executive. Okay, so let's look at this again. Probability Democrat and executive over the probability of an executive. All right, so let's look at this. What's the probability of Democrat and an executive? Well, that's 5 over the total possible, right? The 140. That's this numerator divided by the probability of an executive, Well, that's this 48. There's 48 executives over the 140 total. Okay, so this is the probability of the numerator. This is the probability of the denominator. But look what happens. This is 5 over 140 divided by this, right? This divided by this. Or we could say this times what? Times the reciprocal of this, 140 over 48. And see how the 140s cancel out? And that's all I'm doing. So basically all I'm doing is I'm just writing what those numerators would be, because I know this denominator and this denominator is going to cancel out every time. So that's what's going on there. Okay? All right, next problem. Are events D and E independent? Okay. All right, so let me erase this, and I'm going to come up here. I know the questions are down there or below here, but I'm going to do the work up here so we can see the table while we're doing it. All right. All right. So are D and E independent? So this is part C. All right. How do we show if two events are independent? Okay. If we can show the probability of D is equal to the probability of D given E, or we show that the probability of E is equal to the probability of E given D, okay? If either one of those is true, or if those are true, then that means they are independent, if they're equal to each other. If they're not equal, that means they're not independent. So the probability of D is equal to 0.486. How do we know that? Well, we calculated it right there. And the probability of D given E is equal to 0.104. And we calculated that here. Okay, we're doing this one right here. And you can see that those two are not equal. So that means they're not independent. They're not independent events. Okay? All right, so that answers C, not independent. All right. Now, we got one more part D. I'm going to erase this. We're going to come up here and work it so we can see the table. Probability of D and E. Well, I think we already did that, didn't we? Probability of D and E. Well, what is that? Well, that's the number of successful. Well, how many Democrats are executives? Well, that's the 5 there. So that's 5 over the total number possible, which is 140. And so that is 0.036. And there you have it. And I mean, you can come up here and ask all kinds of questions. You can change the D and the E to the P, W, and I. And it's all work the same. What's the probability of production worker? What's the probability that they're independent? Okay. And it's all done the same. That's how you find the probability if you're given a table. All right. So I hope this video helped. Check out my other videos. Appreciate you watching. Give me a like, share, subscribe, comment. And I will see y'all in the next one. Later.